Okay, good morning. So the only reminder is your assignment number 1 is due to release today. I will try to make it available maybe slightly later in the evening because I'm still finalizing certain details for your instruction. Just want to make it as clear as possible. You can expect to get it maybe sometime between 6 p.m. to 8 p.m. If I can make it earlier, I'll try. Otherwise, you can expect around this time, I'm going to send an announcement to tell you your assignment instruction and the starter code are on the e-class for you to download. You can definitely start tonight, or if you want to skim through the PDF instruction tonight and then start the programming part maybe tomorrow. So between now and later tonight, you still have time to catch up with the basics for recursion. After that, we're going to assume you're okay with the basics. All right. But we can briefly go through what you're supposed to do on the assignment since it's the first one, maybe on Wednesday briefly. So just make sure you actually start properly. We'll talk about it on Wednesday. A very quick recap just about what we did last time, which was very fundamental. So last time we talked about the notion about primitive operations. We talked about what should be considered as primitive operation. Specifically for accessing attribute value for OOP is definitely primitive. And we talk about the special case for method call. So the answer will be it depends. It could be primitive or it could not be. It really depends. What's really inside the body of the implementation for the method. We'll see many examples throughout the course. And we talk about this example in thorough detail by tracing it and also to count precisely how many primitive operations there are. Right? That's something we did. You want to make sure you can really do example like this. I'll try to maybe after this series of lecture on asymptotic analysis, I'll give you a more challenging example. I believe that one involves maybe nested loop. You also want to count precisely. The way to do it will be you have to study the pattern for the loop very carefully and precisely. And you can look forward to it. And we talk about this just one simple exercise that's on the slide. You can do it. If you want to check the answer, drop it in my office hour if you're not confident. But the answer should be very straightforward. And we talk about, okay, so this was the final slides, which I'm going to just switch back to the slides, which is about, okay, let me just make sure. All right, this will come later. Right, so the idea about going from absolute running time to relative running time. We talk about this little t over here. So that's the absolute time which will take a primitive operation to execute in any platform, right? The t may just vary from platform to platform. And the idea will be we want to really ignore the t when we try to talk about two different algorithms. You can see the green one, 7n minus 2 versus 10n plus 3. So these are the two expressions for how many primitive operations there are. Normally, if you want to calculate the absolute time, you have to multiply each one of them by t. But since both of them multiply by t, why don't we just factor out t and only compare the green part over here? It's a very important slide to talk about the transition from absolute running time to relative running time, which we're going to focus on from today. Any question? Anything that's not clear to you? Now will be the time to maybe address that properly before we go on. All right, brilliant. Let's now talk about, let's go on. Today, and possibly part of the next lecture on Wednesday could be a little bit mathematical. We have to review what you guys did, maybe in 1019, about the big O. I will give you just enough that's necessary for this course, but still, you have to pay attention to detail. Okay? Now, let's go start with something that's intuitive. So given the number of primitive operations that's counted, so something like we did before, right? 7n minus 2. This would be just one example, right? And what I'm doing here is you can see I put the exponent over here to be more precise. N will be equivalent to n to the power of 1. And also used to be minus 2, right? You can think about 2 would be 2 times n to the power of 0. If you recall back in the math class, any number to the power of 0 would just be 1. So the way to write this can really illustrate what will be the lower term and what's the highest power term. I'll explain that. Right? So writing in this way can help you in the beginning to see how to drop terms. So we say that n will be the highest power. Okay, you know what? Let me write it down over here. Let me just go directly to the example I wanted to put over here. Let's say this one here. Okay, let me put it down on my iPad, and then we'll talk about it. So it's 7n plus 2n log n. And then plus 3n squared. Okay? You can expect that either you will be given some function like this, or this function may just be derived from the Java code given to you, for which you have to derive the running time either way. We haven't really shown to you how to say, given a Java code, how you can really approximate its running time using mathematical function. That may be something we have to do on Wednesday to really go over some example. But for today, let's now focus more on the foundation for the math. Let's say you're given this, right? Every time you want to do, let's say there are different ways I can ask. One way would be approximate the above running time function. So why is that a running time function? You can take a look over here. N, for example, the n over here is input size. If n is equal to 0, that means we're talking about, for example, empty array. When n is equal to 10, that means we are talking about an array of 10 elements, and etc. N can be arbitrarily large. And later on, we want to talk more about what if n grows infinitely large towards infinity. That's really the nature of asymptotic analysis. That's something we'll get to. Okay? But when we look at this, so there are several terms you want to get used to. Let me just rewrite it again. Okay? And I'm going to be more explicit about the exponent for each one of them. So it's going to be 7 times n to the power of 1 plus 2 times n to the power of 1 times log n. And anytime, if we don't really have the base over here, you can assume it's going to be of base 2, right, for this course. If it has to be of a different base, I will let you know explicitly. Otherwise, assume it's 2. And plus 3 times n to the power of 2. All right? Let's now talk about the different terminology. Let's start with the simple one. The constant over here, 2 over here, and also the 3 over here, they are so-called a multiplicative constant. Easy to see. And if you look at the power over here, n to the power of 1 over here, to the power of 1, and log n, mathematically speaking, you can think about log n is a lower power than n to the power of 1. Than 1. I'm going to show you some plots maybe later today, so you will see that if you look at a mathematical function, like in two ways, for example. If you actually got, let's say, a plot over here, this might be, let's say, the value of n. This will be the function f of n. And if you actually try to look at log n versus n, they're going to look a little bit differently, right? N is going to be, for example, just linear. And log n is going to be something growing much more slowly, log n. That's approximately the idea, right? That's what you learned before in the math course. So that's why I'm saying whenever you see log n over here, you can assume log n has the strictly lower power than 1. It's a very important property to see. All right, because log n grows much slower than n. And compare the power 1, 1, less than 1, and also 2. Which one over here is the highest? Apparently, just 2, right? Rhetorical question, so you don't need to answer. That's okay. Okay. But I appreciate that you actually try to help. Over here, so by comparing, this will be the so-called highest power. On the other hand, what will be the lowest power? Guys, now this time you can tell me, what's the lowest power, please? Log n? Okay, that's very good, but this example here in some ways is a little bit more complicated than that. Notice that there is a multiplication over here. If you got multiplication over here, that means you're going to put Think about, yeah, you see what I mean, right? Let me be more precise. So that's why I want to talk about this example rather. If you consider this guy here, because they are not really being added up, so you cannot consider them separately. You have to compare them together. This is almost like n to the power of, we got 1 here, and plus something we said is strictly less than 1. Right? So you're going to get n to the power of 1 point something, mathematically. Right? So the answer would be, you compare 1 versus 1 point something versus 2. Apparently, this will be the highest power. And this will be the lowest power. Let me write it down, and then I'll take your question. Think about this one over here is the lowest term. Yes, you got a question? Very good. Okay. And of course, this one here, the blue one, this one here is not really the lowest, but it's still lower than the highest power. So you can call that a lower term as well. Any term whose power is strictly less than the highest power would be considered as a lower term. All right, lower term. Are we okay so far about different terminology here? It should be straightforward, right? And the idea would be, whenever you're trying to approximate the running time, what can you disregard? You can disregard by taking all the lower term. The highest term, asymptotically. I'm telling about this tip. Let me prove to me. Otherwise, I can do that maybe to start you fresh next time with proof. But let me write it down, and then I'll take question. So this highest power over here is what really matters when you want to understand asymptotically about this running time. This is what matters, the highest power. Disregarding all the lower term. All the lower term. Let me draw a little bit connection to what we said last time. Remember when we count the number of primitive operations for find max, it was something like a 7n minus 2. If you look at 7n minus 2, that would be important if you want to know precisely how many primitive operations there are. But if you just want to evaluate asymptotically, how good is the algorithm? 7n minus 2, drop the minus 2 because that's lower term. Drop the 7 to the n because it's multiplicative constant. You only got n left. Kind of follow me, right? So n is really what matters for the find max algorithm asymptotically. That's something we have to do very often in this course. Of course, we'll do more concrete example next time. Yes? 7n and n? Not asymptotically. Very good question. Well, we're more talking about, okay, so let me put it aside. Very good. It's a very valid doubt. Oh, sorry. Let me draw a little bit better. If you talk about n versus 7n over here, as we said before, we can just drop the multiplicative constant. So asymptotically, they are just, I would say, in the family of n. Of course, the formal notation will be big O of n. I'll try to define this more precisely, but in the same family. I agree with you. If you consider n being 100, it will be 100 versus 700 already. But we're more talking about asymptotically. If you say the input size is really towards the limits, they are really in the category. If you look at the growth, they're really the same. Yeah. But I wouldn't say your concern shouldn't be brought back at some point. Let's say beyond this course, what we taught you in the lecture will be more or less like a theory on the textbook. But let's say if you really are facing an algorithm between 7n versus n, if your input size is not really towards infinity, and then you have to somehow expect what will be the average size of my input. In that case, maybe n will be actually better than 7n. But for this course, we talk more about mathematical theory. That's something we have to focus you on. After the, beyond this course, it can be more flexible depending on what you That's something I can tell you. Okay. It's a very valid concern. But for this course, we focus more on asymptotic. All right, let me move on. But this is just the very first example, guys, before even present to you the theories. But we're going to look at that. Just that one, if you are following, very good step. Okay, highest power and etc., right? Okay, so we want to approximate the running time as a function on the input size. So it's going to be f of n. So whenever you see f of n, it's really about the running time of some algorithm. Okay. And then given the high-level description, in our context, it will be more or less Java code with a little bit tolerance, as we said before. But you can assume what I give to you should be very close to 100% valid Java code. And we want to give the f of n, and then it's going to be, yeah. So for example, if you see over here, if f of n is equal to 7n minus 2, that means if you're given n being 10, so that means you will get 70 minus 2, 68 primitive operations, right? I'm just plugging in the number to show to you. So we got different example over here, just a category of function. Let's now take a look. So we got constant. F of n is interesting over here, right? What does it really mean? If you algorithm, let's say f of n, let's say running time. If f of n is equal to 5. This one could be confusing here. What does it really mean over here? That means when the input size is maybe 0, the number of primitive operation will be 5, according to this function. And if the input size is 10, it will still be 5. If the input size is 1 million, for example, it is still 5. So that's why it stays constant over here. So this is the only one where the running time is independence of the input size. And if you look at the input size, in this case, 0, 10, and 1 million. Doesn't really matter. So if given that your algorithm is programmed correctly, remember correctness is always the first priority. Given that correctness is already guaranteed, if you can get a f of n equals constant time algorithm, that's the best case. That means your algorithm is so good, so efficient, despite the input size. Yes? Mm-hmm.
There's a really big gap between 100 million.
Mm-hmm. Yeah, I see what you mean. How about this? So when we said, again, back to the old question, let me try to address it a little bit differently. When we talk about n versus 7n minus 2, for example, I agree. Even if you try 1 million or try 2 million, there's going to be a gap. But asymptotically, if you try to use the limit function to see what will be the running time for these two towards the limit, you'll see that they're more or less the same for growth of rate, the same category. So that's more about the mathematical on the paper. But as I said, in practice, you may maybe opt for maybe n as opposed to 7n, maybe. But for this course, we focus more on asymptotic decision. Yeah. I really appreciate the question, but we're just going to distinguish between what we do in this course, more like a theoretical common sense, versus what you might do a little bit differently in the practice. Yeah, I'll take you first. Yes.
Is it the same thing? So would 7n minus 2 be the running time of the function?
Yeah, yeah. So, okay, let me also clarify. Let's be very precise over here. If you remember the find max that we did, algorithm, we say that 7n minus 2, right? Okay. Let's first of all clarify what this is, and number two, how we can treat it as. Number one, the number of primitive operations. For example, if n is equal to 1, that means 5 primitive operations, right? Plugging 1. If n is equal to 10, if you're plugging 1, it's plugging 10, it's going to be 68 primitive operations, right? Are you okay with this? Just plugging in the number. That's number one. number of primitive operation. That's what we counted, depending on the input size. Okay? The more the input elements in the array, the more iterations you will actually have to go through. That's why the more primitive operations you will have over here. Number 2, that's important. This is running time, but not the absolute running time. It's the relative running time because we factor out the little t, right? This will be the relative running time. So any function that we're going to take a look at from now on, so think about they are more like a relative running time function, depending on what the input size is for n. That's what we're doing.
Mm-hmm. To very, very large input sizes, the gap between, let's say, 7n and something like n log n or something like log n is even more substantial.
Yes.
So you say it's in the same class as n.
Yes. I think maybe the more precise way to think about asymptotic analysis is about seeing the growth rate of the functions. I think back in your calculus class, if you want to see the growth rate, what would you do? You take the first derivative. But we don't do that in this course. That'll be a little bit too much. So I'm going to show to you very good. That's a very common confusion. I would suggest the following. Keep that doubts over there. But as we present to you the formal definition on the paper, which is going to be defining how you can prove if a function is a big O of something, you're going to find some proof strategy. Maybe after that, just remember when we talk about choosing between algorithms, that'll be the definition you have to apply. That's a standard. Okay? But even though the two functions might be in the same family of big O, let's say 7n versus 7n, let's say 9n, even that. Sometimes, maybe in practice, you have to choose the 7n as opposed to 9n, but not for this course. Okay.
Is there any? I'm just curious. Is there any real? You know how that's a constant function?
Mm-hmm.
Is there any real-world examples of have we made an algorithm so efficient that it runs independent of?
Well, yeah. Well, of course, I don't really have a very useful on top of my head. Let's say the hello world, right? You print out system out of print line hello world. Or to be more commonly seen in this course, sometimes your algorithm may have different cases. Maybe your case number 1 of some branching condition will be bigger, like a constant time, but other branches may be log n, or other branches might be n squared. So maybe the same algorithm may exhibit different behavior depending on the cases. Yeah. Mm-hmm.
So just like the fine max, in this course we haven't looked at how to calculate the absolute running time yet, right? Like, do you still have
No. Absolute running time, we already covered that in the following sense. Okay. Hopefully that'll be the last one, so I can move on. So think about 7n minus 2. So for the fine max specifically, no, we haven't really measured that. Remember repeat number 1, repeat number 2. There are two methods. We showed to you how you can measure the elapsed time for running the two algorithms. I will also show you a table. That's how you actually measure the absolute running time. Not yet. We haven't talked about big O just yet. So I think I thought it might be nice for you to see the example first before we present to you the formal definition. Yeah. But for asymptotic analysis, we haven't introduced that just yet. Yeah, coming very soon. All right, so the main idea to take from here will be, if you ever want to understand more about the running time here, this could be constant or could be many other options, which I'll show you on the slides. If you want to see how the function is going to grow as the input size grows, you have to plug in different input number over here. For example, from 0 to 10 to 1 million, etc. And then you can see the very nice plot comparing different functions. That's something I'll also show to you, right? It's also on one of the slides. Okay, so what we have, constant, and the next one that's a little bit more expensive is log n, right? Log n is considered as more expensive than constant, but it will be cheaper than linear. All right, so that's a very standard order. And of course, you can see n over here with, I just give you some example multiplicative constant, just 4. It can be anything, okay? And the next one will be quadratic, n to the power of 2, and cubic will be another one. And the more general one will be, which I didn't really put here, it's called polynomial, okay? I think it was summarized somewhere, but in this list, somehow it's missing. Think about polynomial. N to the power of d, okay? Of course, over here, you can say d should be larger than or equal to 2. Because if d happen to be 0, that will be constant. right? If d is equal to 1, it will be just linear. Polynomial usually refers to more about starting from 3, okay? Starting from 2, actually. Okay. All right, so this slide here is just talking about whether you should really focus more on worst case, best case, or average case, right? That's something I touched upon very briefly last time. So the idea would be you want to focus more on the worst case, right? Best case, definitely not. You can never expect the best case is going to occur, even though it might, but not that often. You definitely always have to worry about worst case. We wouldn't really talk much about average case analysis. It's the more advanced analysis technique. But hopefully, as I mentioned before, how you grow the array size, I kind of briefly sketched that last time at the end of the class. Either we'll try to do the exercise in class, or I'll give you guys some nice tutorial video to follow through to do the analysis. It's kind of fun to do that. You're going to use the technical amortization to average out the running time. All right? But what we're going to focus on for, at least for now, will be worst case.
Linear can be cheaper than logarithmic and some physical use cases. Like, for example, I'm not completely sure, but I believe that like if you're working with like a large array, like maybe you're sorting it or something, can linear be cheaper than
No, we say asymptotically, definitely, we talk about like a theoretical sense. If you got something maybe linear over here, it's definitely considered as more expensive than logarithmic. Because if you plot these two functions, you will see at some point linear is going to catch up and then go all the way faster than logarithmic. There might be some small cases where maybe it wouldn't make a huge difference. But the spirits of asymptotic analysis is you don't really be bothered too much by the smaller input size. You're more talking about what about if the input size grows towards infinity? That's really something you want to worry about. Okay? Good. All right, asymptotic analysis, right? Already talked about its essence, but let's go over some slides and then we're going to do some definition. And then, of course, example. Asymptotic analysis, what is that really? It's a method for describing behavior in the limits, right? Limit here is really important. Remember the limit function you guys did, in the calculus course. But we don't really do that much here. And it's really about how the running time of the algorithm under analysis, 7n minus 2 versus maybe log n times n, for example. How the running time is going to change as the input size changes without any bound. That means towards infinity, right? That's why you don't really have to somehow worry too much about when input size is pretty small. That should not be the basis for your decision. Your decision should be towards infinity. And for example, over here, if you see one running time will be n, the other one will be n squared. This is an easy choice to make, by all means, n to the power of 2, because that one is strictly higher power. 2 versus 1, by all means. And this asymptotic analysis will allow us to really compare the relative performance time, right? Because we get rid of that little t. So now we only got relative time to compare the performance. Okay, so for large enough input, we can drop multiplicative constant and lower term. And that's something we did, right? Just 10 minutes ago for that example. We can drop them. And for example, over here, let's take a look. If you look at running time number 1, 3n squared plus 7n plus 18. Another one, 100n squared plus 3n minus 100. And we talk about asymptotic sense. All you got to consider will be the highest power. What would be the highest power over here by dropping everything else? N to the power of 2. Really? Agree? Okay. What about this one here? Also, n to the power of 2. You drop the multiplicative constant, you drop out the lower term. You only got n to the power of 2 left. So after dropping everything that's irrelevant, we got n squared versus n squared. So that's why they are equally efficient asymptotically. It's important to add that context. Another example would be, let's say this one here, n to the power of 3 plus 7n plus 18. For example, let's say we compare this one here, okay, this one here, and RT1. You might see a much larger multiplicative constant over here, 100, versus just 1 over here. But it doesn't really matter. all you got to do will be just keep the highest power term. In this case, it will be n to the power of 3, right? N to the power of 3 is going to grow much quickly towards infinity than n to the power of 2. So that's why we say this one here, because the running time is going to grow much faster, it's less efficient asymptotically. Right, guys, I know no visualization here, but I thought it's good to mention this example. We'll see lots of them very, very soon on the iPad. Okay? Any concept so far is bothering you still? I need to know. Everybody good? Okay. Okay, just a little bit more notes, and then we can go on to define formally. Asymptotic bounds, there are several kinds. Big O is what we're going to look at only for this course. For your information, maybe in your subsequent course, maybe 3101, the algorithm course, you're going to look at another 2 bounds. One will be omega, another one will be theta. Actually, we might see theta in some cases, but I will mention to you explicitly. For now, just remember, we only look at big O, just the upper bound, worst case. What's really the absolute, sorry, I shouldn't say absolute, that might confuse you. That was the asymptotic upper bound for your algorithm, okay? Okay. And the next one will be to have some definition for the big O. Before that, why don't we take attendance? And then I'll start you fresh after the break, all right? Please get your iClicker ready. We should be good to go. Okay, I'm going to start the class. And then start a poll. And then select. Okay, you should be able to check in. Any issue you might run into, come to the front right away. Once I stop the polling, no argument, please. Okay, I'll pause for maybe 10 more seconds. Okay? Okay, seem to stabilize. Okay, any issue should really count. Otherwise, let me see. My clock is about 10:33. Why don't we take a 3 minutes break? Okay, come back in 3 minutes. Don't go too far, and then we'll start you fresh with the big O. Okay. If you got any technical issue with your iClicker, you can come and do the sign-up sheets. Once we start the lecture again, please, we are done. Question? Yes.
I'm not sure if anyone's late to lecture, but I did this at home. I just don't know if it's right because I'm not sure how many primitive operations are in length.
Yes, yes.
And this, because
Yeah.
these are different, right?
Yeah.
'Cause this one doesn't
Yeah,
have
so
that.
this one has no parentheses. Yeah, yeah, that one should be. Did I put parentheses in my code?
One of them has parentheses, one of them doesn't.
Oh, I should
This
fix.
is exactly
Okay,
how I wrote it.
okay.
Yeah.
Oh, it's different. So this will be some attributes. How about this? Let's talk about during my office hour. We can go over this.
When's your office hour again?
Check the syllabus, and then we'll find
Syllabus,
it.
I'll check.
Yeah, not today, but it's tomorrow.
Oh, it's
yeah.
tomorrow? Tomorrow?
Tomorrow or Wednesday or Thursday.
Yeah, we'll work tomorrow.
If you cannot, maybe send me an email, and then we can maybe set some appointment. Because I just need to go over this
But
with you carefully.
You didn't take this up at the beginning of the class,
No,
right?
I didn't.
Oh, okay.
No, I didn't.
But this is running time is like sorry the
That one should
primitive
be
operation
that should be constant.
This is constant, but
Yeah,
this one is not.
this one we can assume is constant. It's only
Oh, so
getting
then I
the.
just assumed everything was constant, so I just did it how it was.
Yep. If you want to go over that, I can go over with you.
Still linear. This is, would be still linear.
I'm pretty sure it's linear. I'm just not sure about if that's precise enough. If the exact number is really right.
1, 2.
Well, we can talk about it maybe later.
Yeah.
Okay. Yes. Nothing seems to pop up for you. Okay. Yeah. We maybe try to launch the iClicker right away next time. This time we can let you sign.
Am I logged in? Am I in the right class or something? I think I'm not.
What are you doing? That's 4315. Are you in that class or 2011?
think I made a mistake.
Made a mistake? Okay, why don't you sign first, and then please make sure you fix that. Are you sure that's you?
Yeah.
That's you, right? Okay, can you please sign over here? Yeah. Okay, yeah, you gotta fix that. It's not 4315. No wonder, right? Okay. All right, guys, another 1 or 2 minutes, and then we'll get started again. Okay, we'll start in just 1 moment, please. Just get ready. All right, let's get started. Okay, I think it's good to start fresh because what I'm going to do now is to present the very dry formal definition. But I'll try to help you somehow. Is there any memorization included, required? I would say yes. You will definitely have to know the definition, but I'll try to help you visualize what's really being defined over here as we present. Hopefully that will help. But I'll leave it to you what might be the best way for you to really apply the definition to example. Let's take a look. Right? From now on, we're going to refer to f of n and g of n. All right? So you want to understand f of n over here is going to be the running time of some algorithm, number 1. Okay? Number 2, what about g of n? G of n is basically what we call our reference function. Okay, let me just get it straight about terminology over here. The big picture goes like this. If you got f of n, this is the running time function, which will go from input size, the relative running time, which is about approximately the number of primitive operation.
So like 7 minus 2 from 5 max.
Yes, that's right. Relative running time. And this one, yes, indeed. Let me just mention that. For example, the find max has relative running time, which is 7n minus 2. Good. Okay. That's about f of n. What about g of n? G of n is what I call a reference function. In the sense that you may have to do a little bit more manipulation to it in order to complete certain proof. And what do you want to prove? Okay, so you can think about further manipulation on g of n expected. I'll show you what the kind of manipulation is in a moment. Right, given f of n, given g of n, what's the goal usually? The goal is to prove that f of n, I'll try to be consistent with the color I'm using, prove that the running time of n is the big O of g of n. That's a very quick summary about what we're going to do. But you really want to understand the big picture. Otherwise, you can easily get lost in the equation. All right? Let me recap, and then we can go on to talk about definition. Running time will be f of n. There will be some reference function g of n for which we want to prove that in the family of the big O of g of n, it includes f of n. That's basically what we want to do. And one more thing to say, one more, which is also mentioned as a common tips later in the slides. Usually, when you write a big O notation here, you don't really include any lower term or multiplicative constant it will be clearer to you later, but I'll write it down first. G of n here, not including. Does not include lower terms. It does not include multiplicative constant. For example, you wouldn't say big O of, for example, 2 times n. You don't say that because you shouldn't include the multiplicative constant. Also, you wouldn't say something like big O of 2m plus 3. Also, that's not good because you can see over here, the 3 here is a lower term, and the 2 here is multiplicative constant. You don't do that. All you do will be big O of just n. That's all you do. This notion will be repeated again once we have seen the more big O example. Yes? Yeah, I would say let's not go too far. You're talking about something way too advanced.
No, but is that valid, like O v plus e? Like, can you say something like
You can do, sometimes you can do some arithmetic over there if that can make it more explicit about the running time. I'm just now talking about in the cases of the example we're going to see, you don't need to worry. Okay, but of course, if we really have to get to that complicated example, I will mention explicitly. Very good. Okay, let's look at the definition, and then I'll visualize it for you. Okay, let's take a look. Okay, big O of G of n, right? That's something I mentioned. Think about the big O here is a notion about a collection of functions. It's not a single function. Of course, you think about if I refer to just G of n, just this is a single function. However, once I wrap it around within big O, there's a family of function. Okay? There's a huge difference here. And let's now read it, and then we'll define. What's going to be big O of G of n? It's going to be all the functions that can be so-called upper bounded by G of n. How can I show if something has been upper bounded by G of n? We need to do a little bit of manipulation to G of n. More precisely, we have to apply some multiplicative constant to G of n so that its slope is going to change somehow, graphically. But we'll see. But just remember big O of G of n. Number one is a family of function, collection, it's a set. Number two, every member function in this collection here can be upper bounded by G of n. That's the critical thing. And let's see the definition very quickly, and then I'm going to visualize it. If your task is to prove that f of n, do you guys know this symbol here? It's a set membership. Yeah, belongs to or is a member of, okay? So when I say, for example here, when I say f of n is, okay, so this part over here, this part here, some people also say, alternatively, f of n is a member of the big O of G of n. People got different saying of this. You can either say f of n is this family, or you can say f of n is a member of this big O. And this symbol here, I assume you guys have seen that, right, in the previous course about set theory. That's a simple one, okay? Or let's visualize once more. How about that? Think about this is the family of function denoted by big O of G of n. And if I say f of n is actually a member of that, so you're basically saying f of n might just be there. But in order to prove this membership over here, you have to show it. I'm going to show it to you. Okay. And how can we prove it? We need to find two things. One is a constant c. That's a real number. But typically, we just do integer. And another constant, n0. That should be larger than or equal to 1. So these are the two things. Well, just remember there are two things you need to find in order to prove the big O. Such that this will be the equation that has to be satisfied over here. Okay? That's about the definition you need to know for big O. But let's now visualize exactly what's happening here. Okay? All right. What we want to prove is f of n is a member of big O of g of n, right? Just remind you about that nice diagram over here. You always want to keep in mind. This is big O of g of n. And I want to prove that f of n is just a member of that. That's what we want to show. And we want to find two things. One thing is about a constant c that's larger than 0. Another thing is about n0 that's larger than or equal to 1. Okay? So think about the c over here, okay, is really about a multiplicative constant. Multiplicative constant applied to g of n. To change its slope. Okay, I'm going to visualize that. For now, you just got to remember. It's going to be a multiplicative constant. And its purpose is to change its slope for g of n. Okay, that's the purpose. And what about n0? n0 over here is the starting point of the upper bound effects. Of course, I haven't really defined what upper bound effect really is. I'm going to do that now. So what's really upper bound effect? I'm going to take your question in a moment. Okay? And I want you to look at just this equation. Oh, sorry. I want you to look at this equation just for now. Okay, this one here. I got f of n. I got g of n. G of n itself may not necessarily bound f of n in general. So that's why we have to do some further manipulation to g of n by applying a multiplicative constant c over here. And the c here changes the slope of g of n. As long as this modified version of the function here, not g of n anymore, but it's more like a modified g of n. If that one can be larger than or equal to f of n, not necessarily right from the beginning, but starting from a certain point called n0, then in that way we can say f of n is big O of g of n. I said quite much over here, but don't worry, it's in the recording. But I'm pretty sure I said everything right. Okay? But we're going to see visually what's happening here. Okay? So what you guys really have to make sure you understand is about this less than or equal to. This one here is really about the upper bound effects. Upper bound effects. Okay? And very often you need the c here. Oh, you need to find c here, and also need to find n0 here. So these are the two things you need. And I'm going to do visualization very soon. C here and n0 over here need to be identified. Of course, by you for proofs. All right? And let's take a look at this diagram over here, just to get a little bit more intuition. This diagram here is not exactly complete because it shows already the modified version of g of n by applying the c. But I'll try to show you another diagram, which is similar by adding a little bit more detail. Let's start with something a little bit simpler. F of n is a function that's running time, right? This is f of n, which is about the running time of whatever algorithm you're analyzing. And the c of g of n is the modified version. This part over here, the pink one. This one over here is the modified. G of n that can sorry, I'm running out of space, I'll put it here, that can upper bound f of n. However, this statement here is not 100% true. Do you guys see why? I want you guys to look at this. Let me repeat it again. You tell me why it's not 100% correct. I'm saying that this function over here can upper bound f of n. Implicitly, I'm saying for any value of the x or n over here. Is that true or false? It's very important for you to see that at least visually. Okay? You spotted that already. You want to let us know? Yeah.
So yeah, of course it's false because for values prior to n naught, it's not true, but after n naught, based on our definition.
Exactly, exactly. Guys, it's a very important, if you haven't seen that, that's okay. Make sure you convince yourself when you see the slide. It's a very important insight. When we are talking about upper bound effects over here, you know, this is only part of the story. Upper bound effect does not necessarily start right from the beginning, which will be when input size is 0 or 1. Not necessarily. It has to be certain n0. As long as you can show that number there, it's okay. So to be more precise, if you look at these two areas, if you look at here, this part, right before n0, okay? So you can think about, in this case, we are really talking about, if the input size, we talk about n. If n is strictly less than n0, it's not the case. F of n is less than or equal to c times g of n. Because you can see that f of n, oh, sorry, yes, f of n here. Sorry, just got it wrong. F of n is exactly here, right? But it is not really below the c times g of n. It's not. I can see there's a gap. Okay, following? But beyond this point, you can see the running time over here is indeed upper bounded by the c times g of n. You can see the relationship kind of switches, right? It flips. So what I need to do is I will write another point over here. Think about this point here. Starting from n is equal to n0, f of n is less than or equal to c times g of n. Okay, I hope that's clear. It's really important for you to see that. Okay? You need to find n0 and you need to find c, these two things yourself. And I'll show you strategy. n0 here and also c over here ought to be found. Okay? Anything that's not clear? Yes.
So the big notation, it looks like the worst time, like the best time.
Sorry, say it again.
It's the big O looks at the worst case, right?
Yes, big O definitely looks at the upper bound. Yes.
Oh, so the upper bound is the worst case.
Upper bound is like a worst case. Yes. That means upper bound means your algorithm running time cannot go above that upper bound. Yes.
So then I guess the usefulness of defining runtime complexity this way is that it guarantees if something is O of a particular family, something that's O of a higher order family will guaranteed like eventually at some point overtake the lower order family.
Yes, yes. I think your insight is really good, but that's something I will summarize a little bit later once we have done some example. Yeah, maybe I wouldn't repeat it for now.
Also, the C that we choose, do we have to pick it like arbitrarily, like a random?
Right, right. In order to pick the valid values for M0 over here, the starting point, oh, sorry. In order to pick M0 here and pick C here, there are two ways to really do it. One way would be you can draw some table to find the earliest part, earliest timing for that to happen, number one. Well, number two, you can actually try to apply some theorem. There's some proof strategy to really use. That's something I'll mention as well. Let's do one thing at a time, okay? We're good? Okay. And the example that we can try is like this. Let's say if AM plus 5 is the running time. N over here is actually some reference function, if you remember, right? This is the reference function. Okay, I'm going to switch to another page very quickly, very soon, just to put these two examples into the more detailed context so you can see exactly what we're doing. We'll do it once. Okay? And what we really want to do is to prove that f of n is a member of the family of big O of g of n. That's what we want to prove, right? Of course, we need to find the c here, and also we need to find the n0 here. Okay? Let's take a look. Let's look at some slideshow, and then I will try to switch back and show to you more. This is just some terminology about how you can refer to big O of g of n. You can either say f of n is in the big O of g of n, like a membership, right? You can say it's a membership, right? Membership sign. Or you can say f of n is big O of g of n. That's fine. But you cannot say f of n is g of n. It's different, right? Then finally, you can also say f of n is order of g of n. You might see that in the more formal context, maybe in some textbook paragraph. But I think I'm referring to 1 or 2 or 3. Either way is okay. I might just say this one here, just easier. I just say f of n is big O of g of n. Okay. And that's the diagram I just explained to you. That one is good. And let's say this. Let's say your task is to prove that the function an plus 5 is big O of n, right? Number one, something you want to imagine to yourself. If the reference function g of n equals n, you can see n over here, this function alone, without any further manipulation, cannot be used to upper bound an plus 5. It's guaranteed n itself is never going to stay above the an plus 5, right? Mathematically. But we're going to see that. You will need to somehow choose a c, and cn c multiplied by n itself is going to modify the slope so that it can catch up with the growth of f of n. That's something we're going to see. Before that, I want to show you some intuitive way to solve the problem, which you can try. You can simply try to draw a table. What we really want to find is the c here, multiplicative constant to n. This will be the upper bound effects, right? You can see an plus 5. This will be the running time function. N here alone is a reference function. C will be something we want to identify very soon. N0 is where the earliest point is for the upper bound effect to start. And let's take a look. Okay, I'm going to put n, an plus 5, and 9n. So here we're just telling you, okay, what about you try c is equal to 9? Of course, you can try other multiplicative constant as well. Try something you think that makes sense. For example, if you just try 8, 8 may not be good enough because 8 here, but somehow you're missing the plus 5. So maybe choose something a little bit larger. Okay? Let's say if you want to show that 9, c equals 9 is a good one. How can we show that? You want to show that c being equal to 9 is going to have the upper bound effect at some point starting from n0. Let's see what the n0 is. Quickly, guys, just understand the first row, and the remaining row should be quite straightforward. Is this row showing the upper bound effects? Because an plus 5, our running time function here, is not less than or equal to 9n, right? If you just plug in the number n being 1, an plus 5 will be 13. 9 times 1 will be 9. So 13 less than or equal to 9 is not the case. Why am I saying this? Because this will be quite important. Sometimes I might just give you, say, okay, if I choose c equals 9, then n0 can just be 1. Is that statement true or false? False. Because the corresponding value here, 13 and 9, they don't really satisfy the upper bound effects. All right? Just notice that. What about this, when n is equal to 2? Can n0 be 2? Also no, because 21 less than or equal to 18 is also not the case. All right? What about 3? 29 less than or equal to 27 is also not the case, but we're getting closer. What about 4? Also no, even closer. And 5 over here. You can see 45 less than or equal to 45. It seems to be a very promising one. But you want to do a little bit more, just make sure the upper bound effects carry on. If you go for 6, seems to be promising because 53, and this one upper bound effect is even more, 54, right? So this is one way to show the upper bound effects. However, this way here, depend if the function itself is simple, you can do it. So I'm going to show you a different strategy soon. Yes?
So before you show that, I'm wondering if it's correct. So in order to find n naught, you just set them equal to each other, and then once you find n naught, would that
What do you mean to equal to each other?
So you would set so if you would guess for like a C, and then you would set like a for this example, right? If you had a C to 9, you would set 8n plus 5 equals 9n, and then after you would find the value of that value of n that solves that, and then that would be your n naught. That's what I was thinking. Is that?
Yeah, of course. I'm not exactly sure why your solution is not exactly what's shown in the table. We can talk about it. So let me just repeat what the solution is being found here. So you try to numerate the growth of the function here. an plus 5 over here is the running time function. 9n over here is your hypothesized c over here, which is 9. And then you're trying to show that n will just grow from 1 all the way until large. You want to find the very first point, which is n0, that's going to start showing the upper bound effect. That's what we're doing. Okay? But there will be a easier strategy for every one of us to really apply, with a little bit caveat. That's something I will talk about. Yes, go ahead.
For any simple linear function like this, c will always just be 1 plus the coefficient, and n naught will always just be the constant.
Not necessarily. It is one way to say that. So you're right. So what you just said was, since 9 here seems to be just 1 plus 8, right? But I can tell you what the tricky thing is. If I give you a different linear function, you might just choose, yes, maybe the c to be 1 plus the multiplicative constant over here, given that it's a linear function. But you're going to still find out n0, which may not be 5. It may be something else. So you still have to actually numerate the table and see where n0 is. The strategy I will show to you, maybe after a little bit more visualization, the strategy will be, we want to have a way to choose c such that n0 is always just 1. That's something we're going to see. Okay? Okay. Yes?
We said that we got the multiplicative constants and like the other term, so like 8n plus 5, the term with the highest degree, and that is just n to the power of 1, which is the same thing as 1. So can we, like for this particular example, can we do it like that?
Okay, what you said was, since I know the highest power over here is simply just 1, can I just conclude directly to big over n? You cannot use that as a proof. What I just showed to you to say drop the multiplicative constant, drop all the lower term is just like a strategy for you to see right away. But what I'm showing to you here is like a proof, which does require some writing. Yeah. So try to distinguish between what you can get some quick answer right away, and also what you can do detail, to get an answer. Yeah, please, final one, and then we're going to move on. Yes.
So for example, what you just said, if we were like proving this on like a test or something,
Yeah.
and the full function had like lower bounds. For example, if it had if that for 8n plus 5, if it had like 2n log n, for example, right, it would be less than just n. No, it would be more than n.
Maybe organize that a little bit, and then let's talk after class. Okay. Yeah. Okay. All right. Assuming that you guys are okay with this first approach, just drawing a table, right? And you guys can also try, for example, over here, we can also choose a different combination of c and n0. Oh, by the way, there's more than one way in general for you to prove if f of n is a bigger of g of n. So choosing 9 and 5 is one way. Can you choose 13 and 1? I'll leave that as a little exercise for you. How can you show that 13 and 1 is really the valid combination? You want to show that the upper bound effect is going to happen between an plus 5 and 13n when n is equal to 1. How do you show that? Use a table like this. Okay? That's my hint to you. Right? Make sure you can do that. What I want to do before doing more example with you is to come back to this guy over here. Oh, sorry, wrong way. This guy over here. All right, this will be the final visualization about the big O idea. I hope this will complete the picture for you. For those of you who found that you're already lost, it's okay. Catch up. All right? Don't expect 100% in the class. Sometimes may just be impossible. All right, so remember the facts we want to show in this diagram. We want to show that, first of all, we want to show that f of n is the bagel of g of n. All right, so this is the fact that we just showed on the slides. And I want to visualize that to you one more time. Okay, really important to see that. And you can see the difference between this diagram here and this diagram here. In the previous diagram, I only show you f of n and the modified version of g of n by multiplying the c. Now I want to put that original reference function here as well, just to show you why the c is so important. All right? Let's take a look. Initially, I want you to take a look at this guy here, which is the running time function. And also this guy here, which is the original reference function without any manipulation by C. This is the reference function. And what you need to conclude from this diagram over here is, if you look at these two, just these two, the conclusion is f of n is never upper bounded by g of n. I'll write it down a little bit more formally, but you can see that f of n is always above g of n, always. F of n actually got the multiplicative constant a, so it's actually steeper than this function here. Also has some constant over here. That means it's also higher. Without modifying g of n, just by itself over here, it's never going to upper bound this function here. I hope that's clear, right? Important to see that. So, to put it more formally, there is not such n0 such that the f of n is less than or equal to g of n. You can see here I didn't put any c. So in that case, g of n can never upper bound this function over here. It's exactly the flip relation. That's number one to note. So what does that mean? That means we need such c to modify the slope of this function over here. That's what we need to do. Right? And how do we modify that? The way to modify that is by multiply the g of n over here by some multiplicative constant. In this way, we got 9, right? So this is 9 here is the multiplicative constant. Changing the slope of g of n. Right? So now the final function to look at is like this. If you look at the blue one over here, if you compare the original g of n and the modified g of n by using c being 9, you can see the difference, right? We basically change the slope. That's really important to see the inside visually. Okay? And then, is the blue function over here always going to upper bound the f of n? Is it always? Not really, right? So that's important to note. So that's why both c and n0 are important. Once you choose the right c, you have to really find the earliest point of the upper bound effects where it starts. Okay? Let me write it down over here. You can think about this one over here is the earliest point. Earliest point, which is n0, where f of n less than or equal to c times g of n starts to happen. And of course, starting from over here, the upper bound effects does happen, so it's true. Before here, the upper bound effects is false. It doesn't happen. Right? Do you guys see why?
Yes.
right? Okay, just want to make sure, because you can see here, compare this function over here and this function over here. Before this point, you can see the input function is actually over here. The input function is actually larger than the reference function, I mean the modified reference function. So there's no upper bound effects. But beyond this point, indeed, there is an upper bound effect. Right? This one just another angle to see what's happening over here. Guys, any question conceptually? I just want to make sure it's straight to your mind. Otherwise, you might just get confused later. Right? We do have about 10 minutes. Let's now waste time. Let's do another. We might just have more example for you. Let's take a look. Okay. Okay, so the function, that's what you want to prove over here. Okay. This one here, I'm just going to tell you the strategy. So for today, maybe I wouldn't do the proof. Let me start you fresh with the proof on Wednesday. So you wouldn't have to worry too much about the proof. Let me tell you the strategy right away. Okay. And let's look at the strategy first. Okay, here. Okay, this is something we'll prove on Wednesday. For now, just understand the strategy. If you got a running time f of n, which could be n0, n1, all the way to n to the power of d. So d here is highest power, just in general. And how can you prove that big O, f of n is big O of n to the power of d, the highest power, right? The way to prove that is always this strategy that works about 99% of the time. The 1% is something you have to always check if that's the case. But we'll do example. And what will be the n0? N0 always 1. That's convenient. That means you don't have to draw so many rows in the table. What about the C? It will be the summation of the absolute value of all the multiplicative constant. The absolute value here is really important. Remember, we got 7n minus 2. In that way, the multiplicative constant is minus 2. But I don't really use minus 2. Use the absolute value of minus 2, which will be 2. This is what you should know before Wednesday. Remember this strategy. Just for now, just remember. But you might just find it so natural later. We're going to do lots of examples, don't worry. But for now, let me just talk about this one here. And for this one here, do I have that over here? Give me a moment. Okay. Let me write it down, and I'll show it to you. And then we'll do the proof next time. And we can do a few more examples. Take a look at this guy over here. Okay. And we'll see how to apply that. I'll copy that to my notes. 5n to the power of 4 plus 3n cubed plus 2n squared plus 4n. Yeah, I know. I'm just copying that, so that's why I got to look at that. Yeah, that's why. Don't worry. There we go. All right. 2 things. Okay. Number 1, several things. I shouldn't say 2. This is the running time function that you're given, right? Presumably. Number 1, we guess, let's say, because this is the highest power. So we'll take a following guess. F of n is the big O of n to the power of 4. That's only a guess. That's not a proof. How do we prove it? We're going to prove it by using the strategy I just showed to you. Let's do it the first one. Okay. Okay. And we're going to prove by using the following strategy. And in order to prove it, you got to choose what the C is, and also choose what the N0 is. By using that strategy I just showed to you on the slides, N0 almost always will be 1. Okay? What about C here? It's going to be the absolute value for all the multiplicative constant. And if you think about this term over here, it's really like a 1 times n to the power of 0, right? So you can also see that very clearly. So you wouldn't forget about that one. So it's going to be absolute value of 5 plus absolute value of 3 plus absolute value of 2 plus absolute value of 4 plus. And I'm writing this down explicitly, even I know they are positive. They wouldn't make a difference. But just in case they are negative, you wouldn't forget to put the absolute value. All right? 8, 10, 14, 15, right? Awesome. So there you go. That's your proof. Simple as that. For this one here, we don't really have to worry about it will fall into that 1% exception case. We'll see one example there. But just always remember, once you have got this one, always check to see if that's really the case. I'll show you how to do the check a little bit later. Are we okay with the first example here? Okay, very good. Thank you. And as a promise, I'll show you the proof. Feel free to go over that yourself, but I'll do that from scratch with you. Very nice, simple proof to do next Wednesday. 5 minutes, guys, please. 5 minutes. No more, no less. I just want to make sure I can use up your time well. 5 minutes. And this will be a property which I will also try to go over with you maybe next time. I think today, since you already learned the definition, you just need to see more example. I think that's what you need. So what I would need to do is, for this slide here, I got maybe about 4 to 5 different examples. I would suggest try not to look at the answer just yet. Print out the slides, cover the answer, and try to see if you can solve them. Let's do as much as possible today, and then we can finish the rest. Okay? The first one. Oops. All right. So let's say the question is, most likely I'm going to phrase this way in the test. The problem is, state and prove the asymptotic upper bound of the above function, or I might just say f of n. So this is more or less how I'm going to phrase it formally in the test, more or less. So that means there are 2 things you got to do. Number 1, state what it is by guessing. Number 2, prove it, right? 2. And let's assume that we're going to use the strategy that you guys had before. You already know. We're going to prove it next time. All right, different parts. Let's say this is part 1, and this will be part 2. All right, let's try to do both of them. Okay, I got 3 minutes, so let's only finish this, and then we can do the rest next time. Okay, feel free to go ahead. Do the rest before I walk you through on Wednesday. What about, guys, what about number 1? What would you say? It will be big O of n squared? Anybody object? N squared, right? Very good. Very quickly. Power 2, n times log n, we talk about it. It's like a 1 point something. And this one here is 1. This here, power 0. So highest 1, 2. Very good. That one's easy. The answer should be big O of n squared. If you only write n squared, that's wrong, because I talk about asymptotic upper bound, right? That's asymptotic upper bound. What about number 2? How do you prove it? And of course, to prove it, either you can use that tabular approach I showed to you on the slides, or you can use that strategy. Yes, you want to use that strategy or table? If table, I'm going to let you do it by yourself. C will be 10 to the, 10 to the 10 to the 10. Not always. If I give you some multiplicative constant that's larger than 10 to the 10 to the 10, then it wouldn't work.
I would think it high.
Yeah, well, you may do that. I wouldn't say that's wrong, but, it's not being very formal. Yeah, very good. I like the thought. Yeah. How about this one here? So, proof by choosing. So, guys, bear with me. I might just run over 1 or 2 minutes. Or maximum 1, because I know my colleagues has another class. So we'll see. Proof by choosing. At least let's choose. What will be the C and what will be the N0? According to the theorem that I showed to you, N0 can put 1 first. What about C? Well, you got to put a multiplicative constant, right? How to do that? Absolute value of 5, 3, 2, and 5, right? 5 plus 3 plus 2 plus 5, which would be 15. I believe. Okay. And I'll show you one more thing, and then I'll let you go. You really want to double check, verify that this does not fall into the 1% case where it might fail. Okay. Verify. Basically, you want to show that show f of 1 less than or equal to 15 times n squared. Okay, how about this? When n is equal to 1, because you can see 1 here and 1 here, right? You want to make sure the upper bound effect really starts from there. Funny enough, there will be some scenario where it's not necessarily the case. Okay, let me, you got a question? Yeah, that's something we'll do. Let's calculate that first. Yeah, let's see. All right, let's now do this very quickly, okay? So 5 times 1 to the square plus 3 times 1 times log 1 plus 2 times 1 plus 5. I agree with you. This guy over here will be 0. Agree? Log 1 will be 0 because 2 to the power of 0 is 1. Log 1 is always 0. Doesn't matter which base it is. Okay? And then we got this one over here is going to be 5 plus 2 plus 5, 12. Is it smaller than or equal to 15 times 1 to the power of 2? Right? This guy here. Is it? Indeed. So check. So that's fine. So guys, this verification process is really important, especially if your equation involves log. I will show you an example actually on the slides that in some other case which involves log. And 0 equals to 1 is not right. You gotta be careful. Any question? Hopefully everything's clear. I will tell you very quickly the plan between now and Wednesday. Tonight, I'm gonna release assignment number 1. I'm sure you will have fun with the recursion. And then on Wednesday, we're going to finish off the mathematical definition example, and then we'll apply this to Java code. That's really important. And then we move on to the next lecture. All right, thank you. I'll see you on Wednesday.